Up next, we're going to continue with some more general examples of things that you should be able to do in Chapter 5. First example in this video states an exam consists of 12 multiple choice questions. Each of the 12 questions is either right or wrong. There's no partial credit. Suppose the probability that a student misses fewer than 3 questions is 0.48, and the probability that a student misses 3 to 8 questions is 0.30. I want to find the probability that a student misses these probabilities here. I'm going to start by figuring out my sample space. I don't have 100% accounted for already, and I know that because I have 0.48 or 48%, and I have 0.30 or 30%, so that totals to be 78%. So there's still 22% missing that I need to find. So here I'll mark my missed questions, and here I'll mark my probability. So a student could miss fewer than 3, not 3, but fewer than 3. That means the student could miss 0 questions, 1 question, or 2 questions. So the probability that a student misses 0, 1, or 2 questions, that is 0.48. Says the probability that a student misses 3 to 8 questions, so 3 to 8 in the missed question column, that is 0.30. 3, 4, 5, 6, 7, or 8. Again, this is only 78% of the sample space. These aren't the only possibilities. Since there are 12 total questions, a student could miss 9 of the questions, or 10, or 11, or even all 12 of the questions. So there is a third possibility, 9 to 12, and that's where that 0.22 comes in. Again, the sample space has to add to be 100%. Everything has to be taken into account. So if you take 0.48 plus 0.30, that is 0.78. And then 1 minus 0.78, that's where I get my 0.22 from. And now that I've got this filled in, I can answer these questions. A is, what's the probability a student misses more than 8 questions? So more than 8 would be 9, 10, 11, or 12. We know that to be 0.22 from this third row. 3 or more questions means a student could miss 3, 4, 5, 6, all the way up to 12. It's both of these bottom rows. It would be the 0.30 plus the 0.22, which is 0.52. And finally, regarding probabilities, C asks, what's the probability that a student misses at the most 8 questions, or 8 questions maximum missed? So no more than 8. So a student can miss 0 questions, 1, 2, 3, 4, 5, 6, all the way up to 7 and 8 questions. It's really these first 2 rows together. The 0.48 plus the 0.30, which is 0.78. At the most means that number and below, so 8 and below. For part D, which 2 events are complementary? Recall that complements add to be 1 or 100%. Parts A and C are complementary. 0.22 plus 0.78 would be 1, would be 100%. It also makes up the entire sample space. More than 8 questions, and at the most 8 questions. Next example deals with a type of probability we haven't seen yet, and that is empirical probability. We've generally relied upon theoretical probability up to this point in our Chapter 5 lectures. This is empirical / experimental probability. And this is what occurs when you actually roll the dice a certain number of times, where you actually flip a coin a certain number of times, like we're about to do here. It says, example 2, a fair coin is flipped 8 times. It's fair, so that means heads and tails are equally likely. Since no coin is available, we're going to use a random number table, which I have down here, to simulate the coin being flipped. If an odd digit appears, a 1, 3, 5, 7, or 9, the coin is said to land on heads. And if an even digit appears, that's 0, 2, 4, 6, or 8, the coin is said to land on tails. We want to use the second row of the random number table to simulate the 8 flips, and then note the empirical probability of tails. Well, theoretically, should be a 50% chance we get tails and a 50% chance that we get heads. But that's not always the case. If you flip a coin a few times, you're not always going to get 50-50. If you flip a coin 10 times, you might get 5 heads and 5 tails, but you also might get 4 heads and 6 tails, or 3 heads and 7 tails. It's not always going to be a perfect 50-50, and that's where this empirical probability comes in. So using my second row here, it starts with a 1, 7, 5, 1, 6. Well, 1 is odd, and 1 represents heads, so it would start with a heads flip. 7 is odd, so that's heads. 5 is odd, that's heads. Another 1, so that's another heads flip. And then finally we get a 6, an even number, so that is a tail. So in the first 5 flips, we've got 4 heads and a tails. Then we just move over to the next set of 5. We've got these gaps here, so it's easy to keep your place. 6, that's even, so it's tails. 9 is odd, so we're back to heads. And 3 is odd, so we're back to heads. And that's where I stop, because I only need 8 flips. I have 8 total here. We want to know what's probably we got tails. Well, my probability of tails, based off of this, there were 2 tails out of 8 flips. That's 1/4 or 0.25. So empirically, tails showed up 25% of the time. Theoretically, it should show up 50% of the time. And this is because we don't have a very large sample size. If you were to keep going past the 3, you've got a 2 and an 8, so we get another tails. So that would increase your probability. You would have then 4 out of 10, which is 40%. It's closer to 50%. And as you increase your sample size, you should get closer and closer to your theoretical probabilities. And that's known as the law of large numbers, that as you have a large sample size, as you perform the experiment over and over again, a large number of times, your experimental probabilities get closer to your theoretical probabilities.